good.
Right. Right. Okay, cool. So I should start, I guess.
Yeah, so we're recording. Is everything set up?
I think everything should be set up. Cool. So, okay, so this meeting is about just discussing some mathematical basics of bosonic quantum error correction. As you may have guessed, I am inclined to focus a little bit more on the GKP code than on other bosonic codes, but I actually also prepared like some minimal info about some other codes. Yeah, maybe we can talk about it a little bit, but we don't have to emphasize too much. You might get more out of me talking about GKP codes than about other things. But yeah, okay. So first question, I mean, like all of us know what quantum error correction is in one way or the other. And so effectively, what bosonic error correction does in generality is just realize the goals that error correction is doing, right? Like you have some physical systems given by some more or less real-life Hilbert spaces, and we try to squeeze some qubits into that, right? We try to embed some logical information into realistic Hilbert spaces or realistic physical systems. Yeah. And so one of the realizations that you go through when you take bachelor courses in physics, and that's a bit of a roller coaster, is that maybe once you start to learn about the like hydrogen atom and like start to learn like basic quantum field theory, basic condensed matter theory, and so on, at some point you sort of learn the general fact that everything is a quantum harmonic oscillator. Right? Every physical system, in one way or the other, people manage to approximate using quantum harmonic oscillators simply because, you know, every physical potential has minima, and every minima, assuming it's smooth enough, which is something that you do in physics, like you can Taylor expand, and then it looks like a quadratic potential. Right? And so the premise of physics in this context is just, okay, everything is a quantum harmonic oscillator. Right? And there are some explicit examples. Right, so that's QHEs, for quantum harmonic oscillators. So some examples of quantum harmonic oscillators are electromagnetic fields, where you have an electric field that interacts with a magnetic field and back and forth. Like if you, I mean, sorry, this is going beyond what you said, but the base idea is that you have an electric field that's being created, right? So if you have a change in electric field, that induces a magnetic field. A magnetic field, again, under some change, creates an electric field, right? And so on and so forth. So there's a natural back and forth between electric and magnetic field, which is summarized by the next equation.
Cannot hear anything anymore.
Yes, same for me. I also can't hear anymore.
Strange. Because I muted myself.
Now I can hear you.
Yeah, that's fair because but your microphone is there.
Yeah.
Okay, good. Then I was doing the mistake of muting for a second. Yeah. Because I realized that I was unmuted. I thought, oh, that bad. I'm not muted, but then I muted this one. I'm sorry, but you were talking about bosons.
Okay, yeah, like
in the most critique of boson something very different, right? I mean, right now on the commentation related to my business.
Oh yeah, we're going to get it, right? Like this is like as simplified as it gets, right? Like I would just want to start with some like examples of why we care, right? Like okay, so electromagnetic fields, like as in the fields of light, are examples of such. Other examples are physicists will know what the Lennard-Jones potential is. It's sort of like the potential that effectively exists between two neutral atoms, right? Like based on the repulsion of the electrons. And apparently tardigrades are also quantum harmonic oscillators. So yeah, so they're everywhere. Okay, so what is a quantum harmonic oscillator? So I'm going to write down the Hamiltonian for a LC oscillator, right? That's the thing that physicists learn. But then I'm just going to abstract away from the LC oscillator. So what we have here is that we have two metal plates on the right-hand side. So they're facing each other,
Yeah.
you can have some charge building up. Like if some positive charge on one end, negative charge on the other end, they attract each other, but since there's a gap, they cannot go beyond this thing. Right?
Okay.
Like the other motion that you can have is that these charges can flow through the inductor on the left-hand side, creating a magnetic field, which pushes them back.
Okay.
So there's going to effectively, if you start the thing with some initial push, there's going to be a very initial back and forth between charges and fluxes that oscillate. Parallel
It feels like a mechanical oscillator where the potential energy is going to kinetic energy back, right? When
Yeah,
you go
exactly.
to the playground,
Yeah.
as you truly often do.
Exactly.
Um,
All that this is a swing.
It's
Okay.
Like
Yeah.
it's a quantum version of. I mean, this not yet quantum version, but it's going to be a quantum version of it.
Okay.
Right. The Hamiltonian of this, like I was just saying charges because like I drew the electrical circuit here, right? It looks like this. You have the charge that lives on this condensator on the right hand side on the capacitor squared plus the flux that goes here through this inductor squared over the inductance itself. Right?
So C and L here are
These are just parameters of the capacitor and of the inductor, right? Like just some parameters that quantify that. All of this is actually not important because what we're just going to do is we're going to just say put Q equals. I mean, typically the convention is the other way around. Maybe let me just say I'm going to put Q equals P, right? And phi I'm going to call, so Q I'm going to call the momentum, phi I'm going to call the position, and I'm going to put C and L to 1. So this is P squared plus Q squared divided by 2, right? So this is how the Hamiltonian looks like. If you quantize this thing, you acquire the commutation relations Q, P equals I, right? H bar is also 1. Everything's 1. Okay. So the next thing that we do, right? This quantum harmonic oscillator, we have some momentum that changes the position. We have some position that, since we have a potential well that creates momentum, we have them back and forth, and these two kind of operators do not commute. So the way to diagonalize this Hamiltonian is to define ladder operators A equals Q plus IP. Like, so the momentum becomes the imagine. You define a complex variable where the position is the real part, the momentum is the complex part. Due to the commutation relationships, these things, A and A dagger, also get a different commutation relationship given by identity, using which you can ultimately just show that this Hamiltonian diagonalizes as A dagger A plus 1/2, and A dagger A, this operator, actually has an integer spectrum. So the A dagger A n is an n where n is some natural number. Yeah. So this is just
maybe because how this is different to qubits or qubits is because of the commutation relation.
Yes.
Right. So the commutation relation can only be realized in an infinite dimensional system, infinite dimensional vector
the one
system.
between A and A dagger.
No, the Q and P or A dagger.
Yeah.
Okay.
It's actually common. A common test I always give my first graders in quantum mechanics to write down the commutation relation and then say that eigenstates and eigenvectors in a finite dimensional Hilbert space. And then I can prove that 1 is 0 in 3 lines.
Yeah.
And I ask them to find a mistake, and they never do.
Okay.
When it happened a single time ever.
Okay.
You can think it's weird. It's like the trace of commutator should be 0. It's like
Yeah, that's a very ugly thing to say.
Because 0 and 1, the 2 qubit states are there, and like there's even common encodings like in harmonic oscillators that would even be used in practice. Like
Yeah, I mean,
1 plus 1 0 type encodings.
yeah. So the annoying thing is that what Philippe says, right? Like it's a curse of infinity. Right? Like if you take the trace here on the left hand side, the trace of commutator is always 0 because things anti-commute and the trace is cyclic. The trace of 1 should be something constant, right? Like, but I mean, of course, this is an infinite dimensional space. The trace of this is ill-defined, and so proving 0 equals to 1 based on this equation doesn't really make much sense.
Gotcha.
Okay. So what do we learn? Well, I mean, what we learn is that this Hamiltonian up here right? That describes this quadratic potential with these like not commuting variables. So I'm going to write down this.
Can I ask
Yeah.
a dumb question? I'm going to ask lots of dumb
There are no dumb questions.
But
Of course, we all know they are, but we shut up about them, right?
No, they're absolutely encouraged. Please.
P hat and Q hat, do I need to care anything about what they are at the minute, other than just they have this commutation relation where they're equal to I? Yeah.
In this context, well, I mean, there's a physical interpretation of those,
Okay.
where like Q is typically used for position and P used for momentum.
Yeah.
Where you can write down a position space or momentum space representation of these operators, where the conjugate part, if you use a position representation, you know, like every state, right? Like every state that lives in the Hilbert space, you can represent, say on the real line, let's say in the position space, but like via some wave function, or in any other complete basis. And with respect to that basis, right? If you use the Q basis, then the momentum operator becomes the derivative. Right.
Okay, but by the way, in mathematical language, I mean, there's a theorem called Stone-Neumann theorem that basically says that you have a harmonic oscillator whenever you have the commutation relation. So that's all you need.
Oh, that is all it is.
So that's it. And then, I mean, of course, there's lots of like physical realizations there, like it can be microwaves, photons, whatever mechanical modes. But mathematically speaking, this is all there is, and uniquely so.
Okay.
Yeah,
Thank you.
that's mainly the thing. Like I say, like it's a more physicsy, or I meant more naive interpretation. If you view all wave functions as wave functions localized over the position basis, or represented by position wave functions, then the momentum becomes a thing that changes position, right? So it becomes a derivative operator.
Okay. I don't yet know what the P basis and the Q basis are.
Oh, it doesn't.
So like just to again what Jonathan said, it's like one of them is the Hermitian generator of a unitary that induces shifts in the value of the other operator. So if I take e to the I P times some value, and I apply that to an x eigenstate, I get an eigenstate of x plus.
Yeah. This is actually important. Let's talk about this more. Okay, so let me define a ill-defined basis.
Okay.
Okay, I'm just gonna. So my position should be some physical quantity that's measurable, right? It's a position of a particle or something like that, right? Or it's a charge or current or flux or something. It should be something physical.
Okay.
Right. So we expect this thing to be an observable. So it should be Hermitian, and you should be able to measure this in some way, right?
Okay. Yeah.
Measuring just means, okay, you say do a projective measurement, you're collapsing it onto some eigenstate. Okay, so now let me just define eigenstates, which are called Q, right? With eigenvalue Q. Right, these are now just labels, for my eigenstate.
Yeah.
Okay. Now, okay, of course, if I have two different positions, okay, this is sort of a bit nasty to show, but what else can I do? Right, I want the expectation value of a position. Okay, what can I do? I can write down a wave function, or I can write down a state. I can write it as a wave function over the position basis. Right, that's what this means. Like these are now my basis states for the position basis. I assume that they are complete basis. I write down a wave function, and what I want is that I can localize this wave function at point Q prime. This here should be psi of Q prime. So this way, what you require is that the normalization, or is that the sort of orthonormality condition between Q and Q prime becomes delta function. Right?
And another remark to T, this is what I do in my data example. I claim that X are eigenvectors.
Yeah.
And then you immediately with identity protection. When they're not there, this kind of dual space or plot space. But that's not concerned. They're localized.
Yeah. So you sort of want to think about these things as eigenvectors. Of course, like the spectrum is infinite. My integral here goes over the real line. So there are all of these mathematical nuances which are annoying, but this is not so super important for us. Right? Like the main thing is that there exists some basis that labels positions. Okay, and every wave function, which is like just an element of Hilbert space, it doesn't really care about any basis, right? That it should be able to measure the state and like with respect to anything, any observable. So, but you can find a representation of the state relative to a basis, which is now here the wave function.
Okay.
Right, localized in the Q basis. Okay, so what does so let's do this. Let's play a game. Okay, what happens if I e to the minus I alpha p apply this to a state, right? To the state. So this is now the first example of a displacement operator. That's going to be important later. That's why I want to go through these things a little bit. Okay, so let's assume for simplicity that our state was just some eigenstate of the position basis with a position q. I mean, of course, this is a state since the normalization conditions, the delta function is not normalizable. There's some issues with this, but it's like a pseudo state, like improper is the right word. It's an improper state. Okay, so now we're just going to check the eigenvalue of the Q operator on this.
Okay.
Right. Okay, let's do this. I insert an identity e to the minus I alpha p, e to the I alpha p q minus I alpha p. This is now the Q state. Here I can use BCH essentially, or Hadamard's lemma, right? Like the joint. I mean, this here is equals to I alpha p applied to the Q operator. I mean, by x, y minus x equals to the x, y. So this is just the correspondence between the adjoint action and on the V group and on the V algebra.
Okay.
So if we write this out, right, well, all that this is Q plus I alpha p Q plus now you get a whole infinite sum of nested commutators I alpha p where this here now comes in, right? Okay, let's just figure out what this is. This is quite simple. The commutator is bilinear, right? So I'm just going to complex bilinear. So I'm just going to pull out this I alpha factor and it's anti-symmetric. So this is equals to I alpha q p. I have swapped the minus sign in front of this. And this here is a canonical commutation relation. It's just I. Right? Okay, so now what we got? We have q plus alpha.
Okay.
So let me insert this, right? Like what I have now up here is I alpha p q plus alpha acting on the q eigenstate of this q head operator. If I act with an operator on eigenstate labeled by the eigenvalue q, I'm just going to get the eigenvalue. I can remove this head. It should have called this q prime or something.
Yeah.
Right? But you get what I mean.
Mm-hmm.
And I pull this up front, right? Like so all that this is q plus alpha e to this minus I alpha p q. Okay, so now what we've learned, okay, we've learned that this operator has transformed a position eigenvector at position q to a position eigenvector with eigenvalue q plus 1. Right. So, well, I mean, like since we label the eigenvectors by their eigenvalues, this is simply q plus alpha.
Okay, yeah.
Right. So now what this is what also Philippe meant earlier, but like this is the commutation relation defines in the algebra that when you like exponentiate to the group elements, which are these e to the minus I alpha p or q kind of operators, sort of effectively shift the position by whatever amplitude you put into the exponent.
Okay.
So all that this means is that okay, you know, like okay, now we're going to do this, right? Like you have start with some state, right? You write it in the position basis, it's like q, right? So this here labels the wave function over the q basis, and this here just says, okay, yeah, my state is this is the Hilbert space element corresponding to that q basis state. By e to the minus I alpha p applied to size, apply it to it. I'm just going to apply it to this part in the back, right? This is the q, and then I can substitute minus alpha Q. Right? So now effectively what you'll see is that this operator has shifted the wave function from Q to psi Q minus alpha. So if before the wave function was 0 at 0, now it's going to be 0 at alpha. Right? And so on and so forth. So what you've effectively done is you've taken the whole wave function, shifted into the right.
Okay.
Right? That's why this kind of operator we call the displacement operator.
Okay.
Because it takes a state and it displaces it.
Okay.
Right. Okay. Okay. So that's mathematical basics. So yeah, of course we can play the same game along the other question. Right? Like all that we needed was this commutation relationship. So we can also equally define an operator equals IVQ, and we can realize wave functions along the p basis, right? Which again we assume the momentum to be something physical. It should be diagonalizable, right? Like there should be some. If the momentum in this example here corresponds to the charge on the capacitor, then there should be some way to measure this thing, right? Like just measuring the charge. So this should be something physical. There should be more or less eigenstates corresponding to it. So again, you have a spectrum. You have a decomposition into improper eigenstates, which is complete. You can write any state decomposed over that basis. And well, I mean, ultimately, at the end of the day, what you find out now, I have a different sign, but that's because the commutation relationship QP also is sort of biased in the sign, right? Like this Q comma P equals I, not P comma Q. So there's a biasing sign, which translates up to here. P. So P operator over P is P. This is simply P plus V.
Okay.
Right. So we again have the whole same game. Right? Like so whatever kind of operators with these like first order terms in the exponent we define, we obtain displacement operators that take a state and shift it somewhere else. Okay. So okay, so we can generalize this notion and like just define displacement operators. And I'm using a slightly weird convention here. You'll see why in a second. I mean, you're going to see why right away.
Maybe another key comment. I mean, the data operators, they're really like I mean, the while operators, they're really like Pauli's in the screen setting. Yeah. I mean, there's a very close similarity between like such Bosonic systems and discrete Weyl systems, particularly in prime dimension, but in 2 dimensions also to an extent.
Yeah.
And I mean, this goes as far as to the point then that you once wrote a paper on this kind of positive Wigner function stuff, that this can be that quantum computers with positive Wigner functions can be efficiently sampled. That from a modern perspective sounds obvious, but at that time wasn't so obvious. And you wrote this paper both for harmonic oscillators and for qubits.
Okay.
And you invented a notation so that the notation would apply to both. Okay. And that like with one notation, one could really in parallel have the qubit and the harmonic oscillator system in the same framework. Okay. No modification. So this then once you get the translation, you're in business. Okay.
Yeah. Okay. So now what we're gonna all I'm doing now, right, is I'm gonna generalize what we just did. Okay. Right? Okay. What we just did was we defined operators that had this exponential form. We have some linear function in quadrature operators, right? Yeah, and that's it. Okay, so how does this look like? I'm going to summarize all of my quadrature operators as a big vector. Right? Now I have n quantum harmonic oscillators, but each live on an individual like single particle Hilbert space or single mode Hilbert space. And I summarize the vector where the first n of these entries of this vector are position operators, and the last n vectors are momentum operators. Okay. Right. So, and of course, I mean, so now this is a very weird vector because we know Q1 doesn't commute with P1. Yeah. Right. And so now this vector contains elements that don't commute with each other, so we won't ever be able to write down a like clean eigenstate of this vector. Okay. Right. But it's okay. Like we don't care. Okay, so I mean, why to do this? I mean, I did this in order to just write down some inner product with some vector. Right? Like now I defined a matrix J, which is just a block matrix with identity on the top right and minus identity on the bottom left. Right, it's the n times n identity, and I defined a 2 n-dimensional vector here. Right. Okay, why is this? Well, I mean, like this is not that super. I mean, there's nothing deep here, but like all I did was I took what we just played around with, and I just generalized it to a big thing for n modes and put everything into vectors. So
the xi are just numbers, right?
yeah, xi are just numbers. Like this is a real vector.
Xi or J?
Xi.
No J's, except for the big one.
There's a big J, yeah. Yeah, and this is really just such that if you take this operator and you conjugate this summarization of all of the quadrature operators, right? I'm going to put this. Let me just write it like this. And I conjugated this vector. All that what you get now is the whole vector plus I have this weird factor that I put in, which you're going to see why, which doesn't matter, plus xi. Right? So now this is the operator that takes the whole vector of quadrature operators and just pushes it somewhere else.
With the notation, I'm a bit unsure. So first of all, I think there's no equal sign in the last line on the left. Like d xi is not equal to the conjugated thing.
Thank you.
And then the x hat.
This is this thing. It's the x hat vector.
I see. It's the same operator.
Yeah, that's a generalized quadrature operator. It's the same operator. Right. And so this is like now the J comes in simply to like order things in the right pattern so that the Q's see the P's and so on. I mean, okay, there's nothing really deep to this. Maybe yeah.
This is saying both P and Q in the single line.
Yeah, I mean just a way to summarize everything. Like that, there's really nothing to this. But like you can, one thing that you can do, right, like is you can, okay, I take this X vector, right? Like the way that this the X on it is it's just X element wise. Q1. Q2. Take a Q1. Voilà. The end. Right. That's what this expression means.
Okay,
Right.
can you scroll up
Oh yeah.
a set just to get this right? So the J appears in the first equation right before the X hat. Is that a J?
That's right.
And
that's right.
The thing before that that's transposed.
Right. Yes.
Yeah.
But that's just to indicate an inner product. Okay. Let me show you what this does. Right. I'm going to write X.
I just want to check where those three things are appearing: the X hat, the J, and the other vector.
Yeah.
Are they all appearing on the left? I can only see two of them. Unless
sorry, where? Here. Oh, I mean this. I just wrote the D operator. Right.
Yeah.
The D operator is this whole thing.
What are you calling the parameter?
Xi.
D xi. And
D xi.
is xi transposed in there, or is that the other?
It's in there. Yeah, everything's in there. Right. Like this.
Okay.
This whole operator is operate. I mean, this is a function.
No, I think the question is where does the xi appear? Because it's some wiggly lines, but hard to distinguish.
Sorry. All of everything in brackets. Here.
That's xi.
That's all xi.
But then what's the thing before the J and the
That's xi transpose. This is also xi transpose.
no, sorry, to the right.
To the right. This.
To the right. That thing.
This is xi.
Okay. So okay, cool.
Right. This is precisely that's in here.
Okay.
So you have two n values,
So just
like
saying,
n q's, n p's,
yeah.
and you have you have n real numbers for the x part, n real numbers for the p part,
Yeah.
and each of these real numbers has by how much do you shift this part.
Right. I mean, all that this does, like this is, I can just one, and I can write out the sum up here. Yeah. And this is just like summing over, I'm now summing only over I equals 1 to n instead of 2n. So all that this does is it's summing over psi I times, right? Like if I take this j, it's gonna take the lower block to go up. So
I'm okay with that now.
pi minus psi I plus n qi. Yeah, that's what this is.
Yeah.
And I can, since it's a sum and also I is labeled different modes, I can just split off and which all like different operators of different modes commute with each other. So I can just like split this exponential up into a lot of like this small displacement operators, each acting on individual modes, right? Like so, this is just to write down a generalized displacement operators that acts on everything, right? Okay, so why is this displacement operator, these kind of displacement operators significant? Well, okay, on first hand, they displace things. That's nice, right? Displacement operators are also special in that they commute only up to a phase. So if I have a displacement operator, d psi d eta, then they commute only up to this phase given by this like J inner product between psi and eta. And this is why we really have to like should think about the analogy to Pauli operators or general Heisenberg Y groups, like which are all just like groups of operators that commute only up to a phase, where the phase is just given by the, I mean, of course, just given by the indices by a symplectic inner product of the precisely the same sort. This group, of course, is also closed, where you get some extra phase, which you don't really care about. Eta plus psi, right? Like, and so the idea here really is, okay, if I have a, like going back to the examples that we had up there, minus I b p e to the minus I u p q, right? Like if I have a state q, I shift it by u, right? This is q plus u. If I shift it again, it's q plus u plus v, right? Which again is the same as simply shifting it once with the whole thing.
If I may say so, sorry,
Yeah.
for the many T comments.
No, please.
But I mean, that's in the rigorous way of writing down the commutation relations. And xp minus px is identity doesn't really work because, as Philip said, there's no operator that would actually literally in any meaningful Hilbert space give the identity.
Yeah.
But you can exponentiate this and then get the commutation relations for the displacement operators, then called Weyl relations, and they're perfectly fine because they're on the unit circle.
Yeah. So
sorry for the math.
No, this is perfectly like this is very important because I mean the point is really that the displacement operators take the sort of like not very well physically justified situation of the operators Q and P, but into like two operators that are sort of physically sensible. Like, because so the one, one other thing that you can say is, right, like I can, of course, you know, like if I have a, say one of these electrical circuits up here, right, and I add I apply voltage, right, or I apply current or something like this. That's like physicists, if you go to that, that's what they make you do. Okay. What really just happens is that you take this Hamiltonian and you're adding a linear term. Okay. Right. That's all that it means. Okay. Right? Like you take this thing, you connect a battery to it. Right. All that happens is really you're adding one of these kind of terms. And this term, of course, you know, like this is a Hamiltonian. I write down the unitary of evolution corresponding to the Hamiltonian induced by this minus I alpha phi is precisely an operator of this displacement type. Right. So this displacement has a very like natural physical implementation.
Okay.
Yeah. I mean, you can also think about having a swing and adding a small motor.
Okay. That's easy.
to the swing. Right. Like that's all that the displacement operator does.
Okay.
Right, but in a quantum way.
Okay. So I'm a bit confused about that second line.
And here?
Yeah. So The first one you're showing that they commute only up to a phase.
Yeah.
The second line,
Oh, so the second time is sort of closure.
I mean, yeah, this line.
Yeah,
Yeah.
okay, so
Why is that still an eta, the rightmost thing inside the D? Is that?
oh, yeah. I'm just saying, if I displace once by xi and once by eta, it's the same as just displacing by xi plus eta.
Yeah, okay.
But unfortunately, there's this extra annoying phase that comes up from, but we don't care about it when we go to buffer, like on a projective Hilbert space, where we don't care about global phases.
Okay.
We mostly don't care. There are some nuances, situations where you may have to care. Yeah, and that's the same as what I'm trying to summarize down here. I take the state, you displace it once, displace it again. Well, I mean, like the net displacement is the sum of the displacement that you put up. Right. Okay. So these kind of so these are sort of the important properties of displacement operators, because I mean, you see that this, maybe I should use a different color, and see that this symplectic inner product up here really tells you, okay, how does the commutation break between these two displacement operators? If this thing is integer, they commute. If it's half integer, they anti-commute. If it's, I don't know, like any other rational number, or right, like you get a different commutation relationship, right? And I mean, ultimately, this is all that we care about. Right? Like we want to, at the end of the day, we're going to want to embed a qubit. Right? Embedding a qubit algebraically means finding logical Pauli operators. So now here we have a way to control how operators commute.
Okay.
Right. And I mean, like logical Pauli operators are just defined by, okay, hey, I have the x and I have the z that anti-commute and that's squared to some effective identity. Yeah, right? That's what Pauli operators need to satisfy. And now we actually have a handle on it, because we have a very clear description of how things commute. Okay. So, but before we get there, another base thing about displacement operators, they form a complete basis. So what this means is that you can have any operator on like any trace class, any like trace class operator, right? So operator for which the trace is well defined. And you can always write this operator in this weird convention that I've used as an integral over displacement operators. So now this is the integral over two n-dimensional phase space. D sub d eta. Right? So what this means, this is now really one-to-one with the Pauli operator and with the block vector. Right? Like you take some operator, for which the trace is well defined. You take the Hilbert-Schmidt inner product with the displacement operator, and you just sum over all the displacement operators with that coefficient. Okay. Right. And this reproduces operator that you have started out with. So this is really, I mean, so this is like really analog. So this again like justifies like the analogy between the displacement operators and the Pauli operators. Right? The Pauli operators form a full basis for a n-dimensional qubit Hilbert space. They have the right commutation relation. Like for Pauli's, they either commute or anti-commute. Heisenberg-Weyl operators on qubits, they commute or not commute with some weird rational phase. And they are closed in the sense that if you multiply them together, you go back to them up to some phase and some shift in labels. Right? That's okay. That's what we have.
So what do the displacement operators look like in the occupation phases?
Oh, that's very ugly.
Okay.
So the
terrible.
Yeah, that's really terrible. I like the other way around. I mean, there are some associated like polynomials.
Yeah. I mean, this is like called the metavector representation.
Yeah.
It's terrible. I mean, it's a chainsaw massacre.
Okay.
Yeah.
Polynomials. I mean, once we wrote, I mean, you might know that we once wrote this paper on like non-Gaussian states from non-inductive models becoming Gaussian through certain evolutions, and we got a convergence proof in the right topology in phase space that this is actually happening. That was observed in experiments that we wanted to prove it, and we managed within a year. And then we spent another year showing that this works actually for states. And when you get convergence in phase space, like in the place where these D's live, that this works in the fog representation. And I can tell you why that was so tricky, but to make that translation, it's really painful.
Okay.
But possible.
Okay.
And they're not Gaussian operators, right? The displacement operators.
Well,
They are.
Oh, they are Gaussian.
I mean,
Yeah,
everything below second order is I mean,
I mean, there's
up to
two
second
first
order
mode
is-
and keep the second mode invariant, so if you say it's Gaussian, it's, and you apply it, the same Gaussian, they just shift it and paste it.
Yeah.
So yes.
Okay.
Right. So so displacement operators you can also I mean I mean that's what this thing up here means, right? Like we take this displacement operator, this here, right? Take this as Hamiltonian times time, right? So like analogous to this like applying the battery to the circuit, right? Like if you just build this Hamiltonian that's like linear in the quadrature operators, it's going to implement this displacement operator. And so since the Hamiltonian is linear, it's a Gaussian operation. The next thing, thanks for the segue, is quadratic Hamiltonians, right? So okay. So of course you can have any mix of linear and quadratic Hamiltonians, but that's a bit more complicated. So what do operations do that look like this? I'm going to write a quadrature operator. I'm going to have some matrix and some other quadrature operator. So now this here, like all kinds of second order polynomials. Second order poly in UI, right? I'm going to assume that M is symmetric. So this is now a like the unitary evolution generated by Hamiltonian with a second order polynomial in the quadratures. Right. Okay. Why do I care?
Why did the polynomial in QP work? QP can you bring down e to the
Sorry. X is
a bunch of
X,
oh yeah, I'm being picked. Yeah, it was a bunch of p's and q's.
yeah.
Okay, and some matrix F.
Right. Yeah.
Okay.
Just some. So the matrix is real. It's symmetric, and so that's easy, right? It can also just be the diagonal identity matrix, and then we just get the product of all of these number operators, sum of all of these operators up here. Right. So what does this Hamiltonian do, right? Like, and in fact, we can play the same game as earlier. It's just an nasty calculation. We can just figure this out. What we figure out is I mean, I'm going to call this U M, say, right? Okay. I take UM dagger, the X operator, UM, right? Okay, we play the same game as earlier, right? Like this is again some nested commutator sequence. So minus I over 2 X. Applied to the X operator. Now this is much nastier, right? Because now you have all of these like you have these Q times P terms applied to Q commutator kind of things that you have to resolve in order to write this. I mean, like just like I mean this nested commutator up here. I don't know, you know how it looks like? I mean it has this. I mean this thing has a structure e to the A B looks like plus A B plus A B plus A B and so on and so forth. Right? Like it's really not. It's really disgusting. But like what you can do is you can like if you compute this, you very quickly see a pattern. You can work on the recursion, and what you'll see is that what you end up showing is that this is actually just e to the j times m, j being this matrix that we found earlier, applied to the X factor. Like this can be explicitly worked out. I don't have a like nice and one-line proof to show this. It's just an ugly calculation. Right? From unitarity of these U's, you will find that M transpose J M needs to be J. Sorry, this is not true. M was just symmetric. E to the JM transposed E to the JM equals to J. Right? Okay, so what is this? Well, typically we summarize these kind of operators by an S, where this condition defines symplecticity. So SP to N R. This really just defined as a set of all operators S in S L to N R or GL, it doesn't matter, it's the same. S T J S equals to J, right?
What are you writing there? SP to.
Yeah, SP to N, the symplectic group, the symplectic matrix group over the reals really is just given by all square matrices of 2n dimension over the reals that has this, that sort of fixed J under this adjoint action.
Yes, okay.
That's all it is, right? Like, and there's a finite set of this kind of operator. I'm sorry, that's not true. There's not a finite set of this kind of operators, but you have to like here classification of what these kind of operators are.
Okay.
So these are the symplectic matrices, and the reason why they're significant is because they have this like really simple linear action on X. If I have another UM prime, dagger UM prime, by which I keep by which I keep changing this, I get a group structure, I get another matrix, right? F prime, then multiplies it. So this really just forms a group so the group of these matrices just really forms a group that tells you how the quadrature vectors evolve effectively under these second order unitary operations.
Okay.
And moreover, what they do is if you have this, now I'm going to write US because it's going to induce this like e to the JMS action. If you apply them to displacement operators, you can work. I mean, there's also like two lines of work. What you see is that the S really just gets applied to the inside of the displacement operator. So this is one-to-one analogous with, this is effectively analogous with the Clifford group. The displacement operators are analogous to the Paulis. In that they have these like clear-cut commutation relationships, they form big bases, etc., etc. And the Gaussian unitaries map displacement operators to other displacement operators with a shifted index. Right? Okay. It's like mapping Pauli to other Pauli strings. That's it. But
yeah,
you shift operator in discrete byte systems, right? I mean, one of the big function and so on is the aggressive function as the expectation value of the shift both here in this world and in the discrete world, and the symplectic Fourier transform is the Wigner function and so on. I mean, all this makes sense both here and there. So if you need the Pauli word as a reference frame, then this works.
Yeah.
Okay.
So yeah, so these kind of operators are going to be important. I'm not going to I shouldn't go too much over time, right? Like I just want to cover some basics.
We can also carry on this tutorial next week as well.
Up to how
happened to the screen. Are you still sharing?
Oh, really? Am I not?
Oh, no, it was fine until 1 second ago.
Oh, yeah, somehow it just stopped. Wait, I'm gonna. No, I think. Yeah, I'm just gonna get back.
Just what happens? The iPad disconnected from the Zoom. I think.
No, but now it should be back, right? Yeah.
Not me, no?
No. Should be me. No, it should work. Yeah. My laptop, my iPad is sometimes a little bit slower when I'm charging it. Do you have that? Like it's sort of weird. Okay.
But you're using a laptop charger for it?
Yeah. Is this too strong for my iPad?
I don't know.
No, I also do this, and for me, it's not getting slower when I charge.
Maybe my iPad is a bit older than.
Yeah, I also don't see how it would make it slower.
Here is more power. Okay, let me check.
Yeah. Okay. So these are symplectic operators. These are displacement operators. And that's like the basic structure of phase space that we care about. One other thing that you will encounter very often that I should just mention before we go to the next topic is, I mean, I was like introduce some basic structure and then I would start talking about error correction.
Then we should probably continue next
week. We can also continue next week. Like, yeah.
It's nice. It's good to have it all together.
Yeah.
And to have a week to digest the basics.
Oh yeah, absolutely. Pleasure.
Okay, cool. Let's carry on with basic.
Right. One thing that you will stumble upon very often, or stumble into very often, is what people call the Wigner function. Right. So earlier we have already seen that we have this relationship that all operators we can just copy this, write, as some complex function, right? Like so, this here is now called. You can call. I keep calling this the character. I mean, no, this people call the characteristic function, right? Or actually, in this case, will be the minus the characteristic function.
Okay.
Since I mean, it's just a function that represents the state. Okay. And this is effectively, and this characteristic function, if you put O being some state, this is a block vector. Right. Only with the nuance that, yeah, there are some subtleties for pupils when you try to, yeah, whatever. Doesn't really matter. Okay, one thing that you can do is you can also define the Fourier transform of this function. Okay, so what we're going to do is I'm just gonna, so this function here, and I'm going to define the function, the Wigner function of this operator at x as the integral over phase space d eta e to the 2 pi d eta trace d eta. Oh. Right. Okay, so this is what people call the Wigner function. The Wigner function is quite neat because it has, I mean, it has a very simple relationship with the displacement operators and rotations that we've seen earlier. Like so what you can show is that if you have the Wigner function of u as rho as dagger, so you have some state rho that you apply some transformation to, right? Like that's x. The Wigner function, this is the same as the Wigner function of the state with s applied to the index x. Right? In the same fashion, if you have the Wigner function of some US displacement operator, d eta rho d dagger eta x, right? That's going to be the same as a shift of the Wigner function by the system operator. So the Wigner function becomes something like a pseudo wave function. Okay. Yeah. I mean, in fact, most people like working with this much more than with wave functions. Well, I mean, so often in Bosonic quantum error correction, the thing that you encounter is that people are going to draw plots of states in phase space, right? And the Wigner function is precisely like the function that facilitates that, right? Because it maps.
You're out again.
Oh no. Okay. What?
Rand's reaction.
Thanks, Amanda.
What she's the alertness monitor.
Well, I mean, she's the person who's not in the room, right? Like, so she'll notice the fastest.
That's right.
Okay.
So is there a way to recognize a pure state from the Wigner function?
If it's Gaussian, right? Like if it's, I know it's the other way around.
Well, yes, I mean, you integrate it and then it says the minimum volume.
Yeah.
It's more spread out.
Yeah.
It's like the smallest.
Yeah. I mean, you can.
I mean, the smallest variance. I mean, okay, so.
The
normalization is one anyway. I mean, sorry, I meant like the smallest variance.
Yeah. Yeah. Right. Yeah. I mean,
but there's a couple of cute observations that not everybody knows. For example, there's no state, no positive operator that has a Wigner function with a compact support. It's kind of function analytic cuteness.
Wait, say again.
There's no state, no positive operator that has a Wigner function with a compact support. Unique tails.
That's interesting. I mean,
if you know a bit of harmonic analysis, it's not so surprising.
Yeah, it's not surprising, but I mean, I was sort of.
Peak is still in the background. So we have.
Yeah. No,
that's. I mean, it's kind of funny.
No, I mean, that's really. I mean, because I was trying to sort of show that whatever states you try to build in phase space, there will always be like interference patterns.
Yeah, well, but think about that. There's no compact operator with a positive Wigner function, and
right.
No, positive operator with a compact Wigner function, and that is a constraint. That
yeah, exactly.
And that really comes from harmonic analysis and like derivatives.
Wait, my screen's out again?
Yes.
Why is this?
I don't.
Yes, it is, but I thought you were not writing.
No, I don't really, I wasn't writing, but I don't really get it. Like it's a bit confusing.
You're not accidentally tapping the red button at the top right of your iPad.
I don't think so. Maybe, I don't know. Right, okay, so, right, where were we? Right, okay, so this is phase space, right? Like you have the Q axis, you have the P axis, and typically people just draw a complex plot of it's a Wigner function. It's generally like a complex function, but it can take complex values. We have for states, you have the normalization, that's an integral over all of phase space. It's really just a trace of the operator, right? So for states, this is just one.
So like how does hermiticity, like Hermitian things with a real Wigner space, right? Like a density matrix will have a real.
Well, the characteristic function is gonna be symmetric, like right, like if you see up here, right, like it's always Hermitian.
Okay.
I takes the whole Wigner function, I take the complex conjugate. It's the same as taking the Hermitian of this displacement operator and of this O. If O stays invariant, then the displacement operator flips its sign. Right, which I can like absorb into the integral, so I can flip the sign of X.
So you're saying Hermitian things are mapped to symmetric things, not real things.
Symmetric characters.
Yeah, I mean the symmetric characteristic function. Are they gonna? Is the Wigner function gonna be real if the?
I thought the Wigner function is kind of pseudo probabilities, and that's why it kind of should be real for.
Yeah,
no, it's not going to be positive because
yes,
quantum mechanics.
Yeah,
is
the
different
function
from classical.
it could be real. Yeah.
Okay.
It's real.
Yes.
Yeah.
Yes. Yeah. I was just saying. Yeah. I mean, I think the proof should really just. I mean, like it takes a complex conjugate, right? Like that. The complex conjugate flips the sign here. It flips the sign here, which flips this and this, right? So this here is assumes it's Hermitian. This here just flips the sign in front of the opal, in front of the eta, which again flips back the sign up here, right? Like so, actually, totally right. The sign up here, the sign flip up here, and undoes the sign flip coming from here. Cool. So yeah, so it's real. Right. Okay. So you often see plots in phase space where people draw states, right? Like for instance, vacuum state 0 is always just some Gaussian block in the middle. If you take a displacement operator, xi, you're going to get a Gaussian block xi.
These are 2D slides, like 3D tokens.
Yeah, sorry.
I mean, it was really imagine it's like 1,000 coming out of the screen. Job, like so you're throwing a circle, it's full with half maximum.
Okay.
Like you draw a bigger function, effectively is the axis, and it's the third.
Yeah.
And typically,
Looks at it from above, if that's what you see.
Okay.
Yeah, so when you see pictures, people will choose some color scheme, maybe red for positive values and blue for negative values. At BBQ, we have this ongoing debate on whether you should use red or blue, and keep like every talk is insisting on its own color scheme. To be fine. But yeah, okay.
So Gaussian unitaries are these US that you introduced. That's exactly Gaussian unitaries.
That's exactly a Gaussian.
And they form the symplectic group.
But plus the
The Gaussian unitary are the mathematical representation of the symplectic group. That's right.
So the displacement of the symplectic group. Okay. Yeah. And the Gaussian unitaries in Wigner space will look like Gaussian.
Well, I mean, okay, so Gaussian unitaries transform Gaussian pure states to other Gaussian pure states. Right. So the Gaussian unitary is gonna like take a blob like this and make a blob like this out of it.
But I mean, like it's also a matrix, right? So you can take a Gaussian, like the trace between the Gaussian unitary and
yeah, that's right.
An operator. So
sure.
You can just like write the Gaussian unitary as a function in space.
Yeah, sure. You can do that. I've never done that. I don't know.
So is that also a Gaussian function? Just complex. We'll have complex entries. But...
let's work it out. Right? Like I don't think this should be so good. Right? I mean, because if I have a Gaussian unitary, right, can I factorize it into
But so, do you mean a Gaussian unitary? You mean by really like a unitary generated by an order 2 polynomial with no linear coefficient or with a linear shift?
Oh, either.
Yeah, because the D is basically taking care of the linear shift.
Yeah.
And then this S matrix is just controlling the quadratic part. And then this combination forms all the symplectic.
Yeah, but I mean, like, I think Andy is pointing out that, okay, displacement form a complete operator basis, so also like quadratic Gaussian unitaries, I can localize, I can represent in this displacement basis. And I mean, like, sure, we can just work out the quadratic function, right? Like I take this US. Is there a unique way? Okay, there probably isn't. Okay, this is going to be more complicated.
But I think there's still Gaussian states, right? For just as a mathematical object, they're just lacking hermiticity, but like.
I'm not sure because, okay, so one thing that you can show, which is shown in the GKP paper, which is the point about.
But they should be, I mean, wasn't there sorry that I bring up a new point, but there is this graphical calculus for CV.
Yes.
Which is not like complete in the same way as like finite dimensional graphical calculus is, because you can't just get rid of loops.
Right.
But you can bend legs and so on.
Yes.
So and I think Andy's intuition is coming exactly from this, like if you have a matrix and then you bend one leg, making it into a state in parentheses, then it should have kind of this.
Yeah, that would make sense.
And this bending legs for sure valid operation in this graphical scheme.
Yeah.
So
yeah, I'm just trying to remember oh yeah, I mean it should still be the case, but I don't. Yeah, I mean because the thing is that earlier I have like, but we need like a generalization of the definition of Gaussian unitary, like relative to what I just wrote down. Because I just wrote down that the Gaussian unitary has a real coupling matrix M, right? And for instance,
Screen's gone again. Every time your iPad locks.
Oh, right.
Maybe. Should we say, by the way, like hard limit at 10 past or quarter past?
You can make a comment.
Yeah,
yeah. In the meantime, while you it's a off-topic comment, but
all right.
It's your uploading. There was a puzzle that I gave to Oliver once because he spent it live on Bosonic channels, and a strange thing. And I asked him, and I gave him a week to answer it. I knew the answer. Okay. He was puzzled for a week, and I said, "Oh, how is this possible?" And then I told him, and then, "Oh shit, yes." Following, you were talking about Gaussian unitaries, right? But there's of course also Gaussian channels, right? Completely Poisson maps that map Gaussian states and Gaussian states, and there's a normal form of them. And you can completely capture them in terms of the map on the level of second moments. Yeah. Right. I mean, a covariance matrix, like a Gaussian unitary would be reflected by gamma, the second moments, is mapped to S gamma S transpose, where S is from the symplectic group. A Gaussian channel would be gamma is mapped to A gamma A transpose plus B for some conditions on A and B so that they're completely positive. And that's well known. These are like glossy channels, like fibers, they're all of this form. Now, if you have a quantum state and you measure on part of it with a homodyning measurement, like measure like X and P and or Q and P in this nomenclature, you also get a Gaussian state. That's well known. That's also much used in quantum information. But the second moments, they involve a Schur complement and hence a nonlinear transformation and are not of this form. So there are two theorems. Theorem one, all Gaussian channels are of the form that I just mentioned, and you can completely classify them as a linear transformation. Second, they are transformations that map Gaussian states onto Gaussian states always and have a nonlinear transformation law. So how can you have a linear classification of all possible Gaussian channels? And then there's another Gaussian channel that is nonlinear. Funny, no?
Yeah, it's weird.
Thanks.
You know what the answer is?
No.
Okay, I'll tell you next week.
Did you figure out? Did you figure it out?
Yeah. Okay, here's the thing. It's true that if you do homodynamic measurement, you can make the trace preserving, and it would be a channel. and would be perfectly valid and would map Gaussian states onto Gaussian states. But for this to be possible, you have to transform the first moments as well. You have to know them, because only then you would know how to shift, how to correct for this, and to shift in the first moment appropriately. If you don't know them, then it's not a Gaussian channel because you shift wrongly. So there's a kind of strange distinction of Gaussian channels that map unknown Gaussian states onto unknown Gaussian states, and the setting where you have to know the state, and known Gaussian states are mapped onto known Gaussian states, but if you don't know them, it's not a channel. It's funny, no?
It's weird.
Yeah.
Okay. Yeah, yeah. Got it.
What is coming up?
All right.
Like, for what?
Well, it depends on what you guys want here. I can talk about cat codes a little bit, but that's not really my expertise. We can, but I prepared like some base overview of cat codes on like base quantum bosonic quantum error correction, or I can talk about GKP, which is much more fun.
Whatever can be most easily explained to newbies. I don't know if like everyone starts with cat codes because they're super simple, then.
Yeah, I would also like to hear about cat codes.
But if alternative,
You have 10 seconds left. Go for it.
but if there's
No, next week.
if there's super simple
next week.
GKP codes that we can start with, then we can do that as well. Just whatever's like
Yeah.
most beginner friendly.
Right. I mean, I put a little bit more focus on the space operators since they're super important in GKP. So, I mean, I can, yeah, we can start with GKP and just time left at the end.
Okay. And I wouldn't mind like once we get to that point, what the differences are.
Yeah.
If we only pick one, if we only look at GKPs, it'd be nice
Yeah.
to know at least what is a cat code, what is.
Yeah, I mean, now that we have like set it all of the base lingo, right? Like that's also why I want to introduce bases, because that makes it very easy to understand how does cat code look like, how does GKP code look like, what are the differences. Cool. Where does quantumness come from? Right, so it's yeah. Okay, cool. Yeah. Next week.
Thanks everyone. Thank you.
Thank you.
Thanks.
Thanks.